So in this video, I'm going to attempt to connect what I know about trig and special right triangles to what I know about the unit circle. So if you need any help remembering how to find the sides of special right triangles, 30, 60, 90, and 45, 45, 90s, then you can refer back to this other video that I made where I give you some tips and tricks on how to remember those side ratios. And if you need any help remembering how to kind of slice your unit circle, I have another video on that you can refer to as well, and just take a look at that. But for now, all I'm going to show you are a couple of ways to put those two concepts together in a way where you don't have to remember that super complex unit circle diagram where everything's just labeled already. It can be a little overwhelming. So I like to remember just a few things on how to take my special right triangles and put them together with my unit circle and then be really successful with trig. Okay, so the only triangles that I really remember when I'm working on my unit circle are 30, 60, 90s, and 45, 45, 90s, of course. And so the main angles I focus on to understand those triangles or place them on my unit circle are pi over 3, pi over 6, and pi over 4. Those are the only ones I really care about. So I'm going to start with pi over 3. So if I need to kind of identify my pi over 3 angle, well, that's just a matter of taking the unit circle, where the top of it is a measure of pi, and then cut it into thirds. So pi over 3 exists right about here. And I'm going to drop a perpendicular and create a right triangle. Okay, so if I'm looking at pi over 3, I know that this angle here has to be 60 degrees because 180 divided by 3 is 60. And so ultimately that leads me to this idea that this is my 30-degree angle. Okay, now when placing the side lengths, it really just becomes a special right triangle problem where I remember the ratios 1, 2, 3 for 30, 60, 90s, and then I put the square root around my 3 and carefully place the numbers from here. So smallest angle goes with my smallest side. The largest angle goes across from my largest side, and then my medium angle goes with my medium side like this. And now I can find any trig ratio that I care about. So if I want to find the sine of pi over 3, it would be the sine of this angle, and that's just opposite over hypotenuse, root 3 over 2. You don't have to memorize. But if I wanted to do cosine, that would just be 1 over 2. And if I want to do tangent, it would be opposite over adjacent, so root 3 over 1. And I don't have to memorize anything, as long as I'm really, really clear about how to set up the triangle to begin with. Okay, let's do the same for pi over 6. So pi over 6 is a matter of taking this entire length and cutting it into 6 pieces, or you can think about pi over 3 cut in half. It would look something small like this. So here's my pi over 6 angle, and I've dropped a perpendicular just to create my right triangle. And then again, this is a 30, 60, 90 triangle where the 30-degree angle is here, and my 60 is right here. And so if I want to remember 1, 2, 3, square root, then I need to place these carefully and go from there. Smallest angle takes the smallest side, and the largest angle takes the largest side, and then medium angle, medium side. Again, the question becomes, do you want sine, cosine, or tangent? Because I could give you all three. Okay, last triangle that I want to kind of commit to memory here and be able to use in my tool belt is the pi over 4 angle. So pi over 4 is exactly that beautiful 45-degree angle. Right here, it's exactly half of the 90-degree angle, and so I know that this is going to be 45. I know this will also be 45, and that causes this to be an isosceles triangle where the legs are the same. Now, if you are familiar with this triangle, it's a 1:1:2 ratio where the 2 takes the square root, and this becomes a side length of 1 and square root 2. So again, the question simply becomes, which trig ratio do you want? Sine, cosine, or tangent? Because I could give you all three. Okay, so now that we have kind of our basic toolkit for any reference angle, I'm going to demonstrate how to determine which quadrant you're in at any time. How do I know if I'm talking about the first, second, third, or fourth quadrant if I want to find the sine of some angle? So I'll go through a handful of examples and show you this. All right, so here are a couple of examples that I'd like to show you how to use your unit circle along with special right triangles to evaluate these trig functions. By the way, I've put my 30, 60, 90, and 45, 90 triangles in the corner just for reference, so I don't forget what those look like. Okay, so first things first, you need to be able to draw your angle. So if I want to find the sine of 5 pi over 4, I need to understand where that falls on my unit circle just by drawing it. So always, 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 I draw a picture. If I want to count 5 pi over 4, well, I know it's going to be past pi because, well, 5 over 4, that's a unit larger than 1. So ultimately, I can still count using fourths, where I would look at this being 1/4, 2/4, 3/4, 4/4, and then 5/4, that winds up right down here. Okay, so now that I know where the angle exists, I'm going to drop my perpendicular and continue to draw my right triangle. Now, as you do this, it's really important that your angle be in the correct placement so that you understand which of your sides are positive or negative. So take a look here. If I want to label my 45, 45, 90 triangle, I know that this is 45s because I'm cutting into fourths. Then I know that I'm working with, this 1, 1, root 2. But notice what's happening here. Be really careful as you label, because when I'm labeling these sides, I'm also thinking about the x-axis and the y-axis. So along the x-axis over here, I know that this side length is going to be a length of 1, but see how it's on the negative side of my x-axis? So out here is actually a length of -1 on my x-axis. And then that's true for the y-axis as well. If I look at the opposite side here, well, this is technically down on the negative side of my y-axis, and that causes this length, this opposite side, to be -1. And then the hypotenuse is always positive, and that's literally a result of the Pythagorean theorem. If I take -1 squared plus -1 squared, then I get 1 plus 1, and square root of that is 2. So your hypotenuse is always positive. Never ever second guess yourself on that. That's a Pythagorean theorem result. It only matters about your opposite and adjacent sides. Are those positive or negative? Okay, so now that I've carefully determined positives or negatives just from the x-axis being negative here and the y-axis is negative down here, I can correctly find the sine of that angle, which is going to be opposite over hypotenuse. Okay, cool. That's -1 over root 2. And if your teacher wants you to rationalize the denominator, just remember that's a matter of multiplying by that radical term, top and bottom. So this just becomes -√2 over 2, however you like. Okay, let's do the same idea for the cosine angle here now. So this is a cosine of 2 pi over 3. Again, begin by drawing your angle. So 2 pi over 3. This is 1/3 and this is 2/3. So my triangle ends up right here. And I drop a perpendicular to form that triangle. And again, really pay attention to which side is positive and negative for the x-axis and y-axis. I can see here this is the negative side, so the adjacent side will be negative, but the opposite side, the height of the triangle, is going to be positive. Okay, to be clear, this is a 2 pi over 3 triangle, which is a 30, 60, 90 triangle, so place your sides carefully. This is my tall, my larger side here. This guy is a 60-degree angle, which means this must be 30. So 30 is the tiny side, which is 1. It's going to be -1 because it's on the negative side of the x-axis. The opposite side will be a positive √3 because it's positive above the x-axis here in the positive y direction. And then your hypotenuse is always positive. So again, never second guess that. The hypotenuse is always positive. To find the cosine of the angle, it will be adjacent over hypotenuse. So this becomes -1 over 2. And that's your cosine of that angle. So again, anytime you're trying to just find the trig function or evaluate a trig ratio for a given angle, draw your angle, carefully think about where each side is positive or negative, and then you are never going to mess this up. Okay, so I'm going to also show you a couple of examples. If maybe you're given that ratio, how do you find the angle back? Okay, so I've chosen 3 different examples, one with sine, cosine, and tangent, in order to show you how these problems can look. So you're going to be asked this question in a couple of different ways. One of them could be saying something like sine of theta, or sine of what angle is equal to this ratio. Or another option is saying like tangent inverse of this ratio gives me what angle, right? So this would ultimately be equal to some theta, and I need to find out what that theta is. So just remember, you can be asked this question 2 different ways, but it ultimately means the same thing. Sine of what angle is that ratio, or the inverse of this ratio is what angle. So just be mindful of those things. Okay, so I need to narrow this down quickly, and here's a couple of ways that I do it. I take a look at the ratio that I'm given, and I decide first, am I talking about a 30, 60, 90 triangle, or 45, 45, 90. So a lot of times you're going to see this square root 2 over 2 situation, but I encourage you to actually go back into thinking about that in a non-rationalized way. So I'm going to think about this in terms of 1 over square root of 2, and I know that that's just the rationalized way of writing this same answer. So why do I want to look at it this way? Well, because I know that 1 and square root of 2 are sides of a triangle, and it's actually my 45, 45, 90. So I prefer to look at these ratios in terms of sides that I'm already familiar with. That's why I hate the square root of 2 over 2 situation. It's not obvious on my triangle. So I would rewrite it this way for myself first. And then also this guy, square root of 3 over 2, well, what kind of sides are those? Do I have a square root of 3 on the 45 triangle? No, it's on the 30, 60, 90. So I know already that this guy is going to come off of my 30, 60, 90 one. Okay, well, what about this? The negative 1 over 1? Or, sorry, I gave it away. My negative 1 value? Think about that as like a negative 1 over 1. So you actually do have 2 different sides going on there, even though it looks like just one side where you're not quite sure what the ratio is. So anytime you have just the number 1, really like remember to think about that as still a fraction. Okay, and then could I possibly get 1 over 1 out of a 30, 60, 90 triangle? There's no way, because this would have to be 2 different sides that are equal to each other, and that doesn't happen here. The only one it happens for is this kind of a triangle, the 45, 45, 90, where I have 2 sides that are in fact equal to each other, that 1-to-1 ratio. Okay, so now that I've given you a couple of ideas how to narrow down what triangle you're talking about, we now want to try to draw it and understand which angle specifically this is. Okay, so for sine, just remember what sides you're talking about. Sine is opposite over hypotenuse. So this has got to be the opposite side over the hypotenuse side. And notice that it's positive. So if I'm talking about an opposite over a hypotenuse situation, and it's a 45, 45, 90 triangle, then ultimately the opposite has to be a side length of 1, and the hypotenuse has to be the root 2, and that means this here is also a length of 1. So what angle is that? That's a pi over 4 angle. But it's also true that if I flip this triangle over here, remember, all I care about is that the opposite side is positive because sine is opposite over hypotenuse. So technically, this triangle would give me the same angle as well. This would be positive 1 because it's a height of positive 1, and then a hypotenuse of square root of 2. Here's the problem with that. That's very unclear to have 2 different answers. In fact, it's not a function if you have 2 different answers. So rather than be super redundant like this, I'm not going to talk about the angles in this second quadrant. It's redundant and repetitive, and it also keeps the inverse function from being a function. So that's what we call restricting the domain. All of my positive sine values, right, positive y-axis, are going to happen up here. I'm going to color this maybe in pink. So sine is always positive up here, because the y-axis is positive up there. But sine is going to be negative down here because the y-axis is negative down here. And that's all I really care about. Sure, I'd get positive signs here and I'd get negative signs here, but I don't want to be redundant, and I also want to make sure that I'm retaining the fact that it's a function. So that's what we do when we restrict the domain. All this is to say is that the answer to this problem right here is pi over 4 and not 3 pi over 4. So make sure that you're mindful of that domain restriction. Okay, the answer is that theta is equal to pi over 4. All right, let's do a similar situation here with cosine. So we've already identified that square root of 3 and 2, yeah, that's definitely a 30, 60, 90 triangle. And now I just need to be mindful of how that looks on my unit circle. So cosine is adjacent over hypotenuse. So I'm looking for an adjacent side that's a square root of 3. If I graph this, the adjacent side has to be square root of 3. So I'm talking like this. And ultimately that means that my triangle is short. So if this is the root 3 side, that means the opposite must be the short 1 side, because the hypotenuse is always equal to 2. And this might beg the question in your mind, based on that conversation, what's the domain for cosine inverse? Because couldn't I have drawn this triangle also? It would have a positive adjacent side of square root 3. Sure, the opposite would be negative, but who cares? Cosine doesn't use the opposite side. And then this would be a 2. So yeah, again, it's the idea that we don't want to be redundant here. Technically, both of these angles give me the same cosine, but I don't want to be repetitive. And I also want to make sure I'm staying in function land. So we're going to restrict that domain. Cosine is going to be positive in the first quadrant because the x's are positive. And it's negative in the second quadrant, literally because the x's here are negative. So that's how you can think about the domain for cosine, is I'm talking about the adjacent side, which is x's. Where are they positive and where are they negative? Okay, let's go ahead and answer the question. This is a tiny triangle. It must be my pi over 6 angle, and so that is going to be pi over 6. Okay, finally, last one that I'll leave you with is this tangent function. We already talked about how I'm looking at a ratio of sides, and tangent is always opposite over adjacent. And so we have a couple of options for where these triangles might exist. I could draw a triangle where the opposite side is negative. Look at how I'm assigning the opposite is negative, but the adjacent is positive. Where would that be? Well, I'm really talking about a negative 1 on the y-axis and positive 1 on the adjacent x-axis. So technically, that triangle would be this guy right here, a negative 1 for the opposite side and a positive 1 for the adjacent side with a square root of 2 going on there. But I can get the same ratio also if I decide to look at this as a positive opposite with a negative adjacent. So that's opposite over adjacent again. But it's going to be a positive opposite. So that means positive height with a negative adjacent side. Something like that. And then this is square root of 2. Okay, so how do I know which angle is correct? I'm talking about our basically like domain for tan inverse. We are ultimately going to achieve all the values that, or all the angles that we need here in the first quadrant, and then also in the fourth quadrant. And that's literally because in the first quadrant, your opposite over adjacent, hey, it's always going to be positive. That opposite side is always positive above, and then the adjacent side is positive because that's true there. And then if you ever need a negative tangent value, that's because the opposite will be negative, but the adjacent is positive. So we ultimately just use anything in that first and fourth quadrant for tangent inverse. And that leads us to conclude, ultimately, that the answer to this problem is negative pi over 4, or the same would be 1, 2, 3, 4, 5, 6, 7. It's going to be 7 pi over 4. And that would be our answer for this tangent inverse for the -1. Okay, so there's a lot going on there, but ultimately the important thing to remember is how do you cut up your unit circle, and then how do you label your special right triangles, and from there you're going to wind up being pretty successful at solving any trig problem you need.